let's use calculus not just to calculate the area under the graph of a function. Let's use calculus to find the area between two curves. Specifically, what's the area between the graph of y equals the square root of x and the graph of y equals x squared? As usual, let's start by drawing a graph of the situation. Here's my plane. The graph of y equals x squared maybe looks like that, and the graph of the square root of x maybe looks like this in red. So what does area between curves even mean? Well, I really mean the area inside this little wing-shaped region here. This point is worth thinking about. That point has coordinates 1, 1. Let's set it up as an integration problem. Well, I can imagine carving this region up into lots of thin rectangles, right? Setting up a Riemann sum. Let's draw some of those thin rectangles in this region here. And you have to worry a little bit about exactly how tall all these rectangles are and how wide all these rectangles are. Well, how tall are these rectangles? Let's just pick one of the rectangles in particular to think about. Let's pick this rectangle and think about it. How tall is it? Well, its top edge is on y equals the square root of x, and its bottom edge is on this orange curve, the y equals x squared term. So the height of that particular rectangle is its top coordinate minus its bottom coordinate, so it'll be square root of x minus x squared tall. And how wide is it? Well, the width of this little tiny rectangle is not supposed to be very big, right? So let's call its width dx, right? I'm imagining that its width is very narrow. It's a very thin rectangle. So that amounts to evaluating a certain integral. Yeah, but which integral? Well, I want to add up the areas of all these little boxes. And these little boxes have heights given by this and widths given by some small quantity I'm imagining to be dx. So the integral that I want to calculate will be the integral of the area. So it'll be the height, the square root of x minus x squared, times the width, which is dx. And then what does my x go between? Well, the smallest value of x here is 0, and the biggest value of x here is 1. So I'll have x going from 0 to 1. So that's the integral that I want to calculate, which will find the area in between these two curves. I can evaluate that integral by using the fundamental theorem of calculus. So the fundamental theorem of calculus tells me to find an antiderivative for this. So let's first think, what's an antiderivative of the square root of x? Well, that's an antiderivative of x to the 1/2 power. But remember my rule for antidifferentiating x to a power. It's x to that power plus 1, so 3/2 is 1 more than a half, divided by that power plus 1, 3/2, so that when I differentiate this, I get back x to the 1/2 power. And I'll just add some constant c on there to give myself the general antiderivative. What if I want to antidifferentiate x squared? Well, that's maybe easier, and it's the same power rule. It's x to the 3rd power, which is 1 more than 2, divided by 2 plus 1, so that when I differentiate this, I just get back x squared. Then I'll add a constant. Now, what's an antiderivative of the difference? Well, it's the difference of antiderivatives. So the antiderivative of the square root of x minus x squared is the antiderivative for the square root of x, which is x to the 3/2 over 3/2, minus the antiderivative for x squared, so x to the 3rd over 3. So there's the general antiderivative for this. Armed with the antiderivative, I can now evaluate the integral. So one way to write that is as follows. If I went to integrate from 0 to 1, the square root of x minus x squared dx, I'll just write down the antiderivative for this, or an antiderivative for this, which is x to the 3/2 over 3/2 minus x to the 3rd over 3. That's an antiderivative for this, plus 0 if you like. And then I'll evaluate this quantity at 0 and at 1 and take the difference. So this is a little bit of fancy notation just for plugging in x equals 1, plugging in x equals 0, and finding the difference. And if I want to emphasize what I'm plugging in, I might write even x equals 0 here just to emphasize that x is the variable that I'm working with. All right, well, let's do that. Let's plug in x equals 1 here. And when I do that, I get 1 to the 3/2 power over 3/2 minus 1 to the 3rd over 3. And I'll subtract what I get when I plug in 0. So I plug in 0, 0 to the 3/2 over 3/2 minus 0 to the 3rd over 3. Well, this is easy to calculate now. 1 to the 3/2 is 1, so it's the reciprocal of 3/2, which is 2/3, minus 1 to the 3rd, which is 1 over 3, so that's just 1/3. And here I've got minus 0. So I've got 2/3 minus 1/3. This integral ends up being equal to 1/3, which is computing the area between the original curves. I hope this problem whets your appetite for harder problems along these same lines, right? You can imagine very complicated area calculations.